So again, if you're trying to figure out the asymptotes of a rational function, for vertical asymptotes, look at where the denominator is equal to 0. For horizontal asymptotes, look at the degree of the numerator and the degree of the denominator, and then it depends on whether the degree of the numerator is smaller than the denominator, the same, or greater than the degree of the denominator. Here's an example. Y equals 3x plus 6 over x minus 2. The vertical asymptote is the line x equals 2, which I can tell even without looking at the graph because the denominator of the fraction, x minus 2, is equal to 0 when x equals 2. And for the horizontal asymptote, notice the numerator and denominator are both degree 1. Since they're the same degree, look at the leading coefficients, 3 on top over 1 on the bottom. 3 over 1 is 3, and so the line y equals 3 is the horizontal asymptote. So as you go off to the right or to the left, the graph is going to level off and come really, really close to, but never quite touch, that line y equals 3. A couple other things we can figure out. Just like with any function, the y-intercept, where the graph crosses the y-axis, is the point where x is equal to 0. So if we put 0 in for x, 3 times 0 plus 6 over 0 minus 2, we get 6 over negative 2, which is negative 3. So the point 0, negative 3 is the y-intercept. And the x-intercept, where the graph crosses the x-axis, is the point where y is 0. So if we put 0 in for y, then we would have to solve for x, but in order for a fractional expression to be equal to 0, the only way that can happen is when the numerator of that fraction equals 0. So when is 3x plus 6 equal to 0? When 3x equals negative 6, so when x equals negative 2. So even if we didn't have the graph to look at, we could tell that the x-intercept is the point negative 2, 0. Oh, and one little warning. Sometimes I have people try to tell me things like the vertical asymptote is 2 or the horizontal asymptote is 3. Now that doesn't really make any sense because asymptotes are not numbers, they are lines. So if you're telling me what the vertical asymptote is, you're telling me what this line here is. And the equation of this line is x equals 2. The horizontal asymptote is this line, and the equation for this line is y equals 3. Let's try some more examples. Y equals 5 over x plus 7. What's the vertical asymptote? Look at the denominator. When would the denominator be equal to 0? When x is negative 7. So the line x equals negative 7 is the vertical asymptote. What about the horizontal asymptote? Well, the numerator is a constant. It doesn't have any x's, so that counts as degree 0. And the denominator has x to the first power, so it's a degree 1 polynomial. When the degree of the numerator is smaller than the degree of the denominator, 0 versus 1, that means that the line y equals 0, otherwise known as the x-axis, is the horizontal asymptote for the graph of that function. Can you tell what the y-intercept is? Well, if we put 0 in for x, we get 5 over 7. So the point where x is 0 and y is 5/7 is the y-intercept. What about the x-intercept? Well, for this whole thing to equal 0, the numerator would have to equal 0, but here that's impossible. The numerator is just the constant 5. That's never going to equal 0, so there is no x-intercept. There's no point on this graph where it crosses the x-axis. So here's what the graph looks like. Notice our vertical asymptote x equals -7. Our horizontal asymptote is the x-axis. We've got our y-intercept here at the point where y is 5/7, and there is no x-intercept. The graph never touches or crosses the x-axis. How about y equals x over x squared minus 9? Vertical asymptote. When is x squared minus 9 equal to 0? Well, there are actually two solutions, two zeros. X squared equals 9, so x equals the positive or negative square root of 9, 3 or -3. So the line x equals -3 and the line x equals +3 are going to be vertical asymptotes for this graph. What about the horizontal asymptote? What's the degree of the numerator? 1. What's the degree of the denominator? 2. When the degree of the numerator is smaller than the degree of the denominator, the line y equals 0, that is the x-axis, is the horizontal asymptote. What's the y-intercept? Well, if we plug 0 in for x, we get 0 over -9, which is 0. So the line 0, 0, otherwise known as the origin, is the y-intercept. And that's also the x-intercept. That's the only point where y is 0 is when x is 0. So here's the graph. We've got vertical asymptotes here, the line x equals -3, and here the line x equals +3. And the horizontal asymptote is the x-axis, and the graph crosses the y-axis and the x-axis at the same time here at 0, 0. How about y equals 20x over x squared plus 9? Vertical asymptote? Well, that would be where x squared plus 9 is equal to 0. But that would mean that x squared would equal -9. So x would equal the positive or negative square root of -9. But that's imaginary. That's 3i. And since there are no real numbers that make the denominator equal to 0, and real numbers are the only things that show up on our graphs, there are no vertical asymptotes. As long as x is a real number, that denominator is never going to be 0. What about a horizontal asymptote? Well, the numerator has degree 1, the denominator has degree 2, and when the degree of the numerator is smaller than the degree of the denominator, the line y equals 0, the x-axis, is the horizontal asymptote. Y-intercept, if x is 0, we get 0 over 9, 0. And that's also the x-intercept. So the point 0, 0 is where the graph crosses the x and y axes at the same time. Here's what the graph looks like. No vertical asymptotes. The horizontal asymptote is the x-axis. So if we zoom out and go way off to the right or to the left, the graph is going to level off and get really, really close to, but never quite touch, the x-axis. And there's our x and y intercept there at 0, 0. How about x squared over 2x minus 4? Vertical asymptote? When would the denominator be 0? When x is 2. So the line x equals 2 is the vertical asymptote. Horizontal asymptote? The numerator has degree 2. The denominator has degree 1. When the degree of the numerator is higher than the degree of the denominator, there is no horizontal asymptote. But there could be a slant asymptote. I'll come back and talk about that in a minute. Y-intercept, 0, 0. X-intercept, 0, 0. Here's the graph. We've got our vertical asymptote here. It's the line x equals 2. We have no horizontal asymptotes. If we go off to the right or to the left, the graph does not level off and approach a horizontal line. And right here at 0, 0 is the only place where the graph crosses or touches the y-axis and the x-axis. Now, the slant asymptote, or the diagonal or oblique asymptote, is the line y equals 1/2 x plus 1. So if you draw in that line with a y-intercept of 1 and a slope of 1/2, that doesn't quite touch the graph, but it comes really, really close to it. And the way you could figure that out is if you take this fraction and you take the numerator divided by the denominator, x squared divided by 2x minus 4. You might have to use long division of polynomials to work that out, but you would get a quotient of 1/2 x plus 1 and a remainder of 4. But that quotient tells you an equation for the slanted line, in this case a line with a slope of 1/2, that the graph kind of straightens out and approaches and has as a slant asymptote. Now back to those examples from earlier. The tennis ball example, we have a horizontal asymptote, the line y equals, or in this case c bar equals 0.25. So that means if we go off to the right, the graph is going to level off, not quite at the x-axis, but a little bit above it at the line where y equals 0.25. So that means that as you make more and more tennis balls, the average cost per tennis ball is getting closer and closer to 25 cents. Look at the water pollution example. In this case, I want to point out that we have a vertical asymptote. The denominator would be 0 when p is 100. So that vertical line where x or p is 100 is a vertical asymptote for the graph. If we zoom out, this part of the graph is going to shoot way up and get closer and closer to that vertical line. So as the numbers you plug in for p get closer and closer to 100, the graph just keeps shooting further and further up, and the cost just keeps getting bigger and bigger, and there's no limit to how big it can get. And the elk example. This time let's look at the horizontal asymptote. The numerator and denominator are both degree 1. And if you multiply this out, it's going to be 40 plus 20t, but the leading coefficient in front of that t to the first power term is 20. The leading coefficient on the bottom, that's the coefficient on the highest power of the variable, is 0.03. So if we take the 20 on top divided by the 0.03 on the bottom, we get approximately 666 or 667. So that means that the horizontal asymptote for this graph would be a horizontal line at a level of where y or in or whatever variable we're using equals 666.7. So in the long run, as we go further and further into the future, this equation predicts that the elk population is going to level off and approach, that is, get closer and closer to, but never go beyond, about 666 or 667 elk.